Okay, let's start. So many thanks for invitation to this mixed format of seminar, and the talk will be about some very nice families of conformal field theories in 3 dimensions, which are one of the best because they describe physics, and they're conformal field theories, and what they have to do with certain extended conformal symmetries that we call higher spin symmetry. And as always, if you have a conformal field theory, you can have 2 viewpoints, just as a conformal field theory, or you can try to view it holographically and see if it gives any advantages here. And so maybe the main message here, or let me start a bit earlier. So like philosophical question I'm going to ask is whether there is some useful infinite dimensional extension of conformal symmetry in dimensions higher than 2, because I think we would agree that in the world of 2-dimensional conformal field theories would have never been so exciting, active, and so on, had it not been for a Virasoro symmetry. And Virasoro gives you the right amount. So it's infinite dimensional, but it's of right dimension because it doesn't overly constrain your theory. You can have lots of non-trivial theories with it, but it's still, well, it's not too small so that it's almost useless. So, in the first approximation, if you ask this question in higher dimensions, whether there is some infinite dimensional extension of conformal symmetry, then in the first approximation, the answer is no. There is no such extension, or if you look a bit more in detail, there is such an extension, and we usually call it higher spin symmetry, but it's not very useful because it is a signal of free conformal field theory. So it tells you very little about actual models you might be interested in. But in the next approximation, there is a certain thing that was called certain beast that was called slightly broken higher spin symmetry by Maldacen and Zhiboyedov, but it's not actually a symmetry in the usual sense. So it's not Lie algebra or Lie group acting somewhere in the usual sense. And it took some time to even understand what it means. But pragmatically speaking, you can just apply this idea, and I'll explain how. And why this concept was born is because there is a rich class of 3-dimensional conformal field theories that are called vector models, or more generally Chern-Simons vector models. They're interesting on their own because they describe physics of second-order phase transitions at least, but they were also conjectured recently to exhibit a number of dualities, in particular 3-dimensional bosonization duality. And this slightly broken higher spin symmetry can explain this duality, at least in the large n limit, and this what I will be talking about. But on a different note, if you try to think holographically and ask what it is dual to, this class of conformal field theories, then natural duals are so-called higher spin gravities, and I will tell you what you can deduce from higher spin gravity about this duality. So as a matter of fact, my talk contains 1.5 proofs of this 3-dimensional bosonization duality. Okay, so accordingly, the plan is to introduce Chern-Simons vector models and bosonization duality, then explain a little bit like what people learned about these models and dualities from slightly broken higher spin symmetry, in particular to explain how to see something like this. It's not a symmetry again, it's just maybe wrong wording, but it was called symmetries. So how to see that something nice and infinite dimensional constrains your correlation functions. And then I'll jump to anti-de Sitter space to tell you more about this duality from holographic point of view. And then at the end, I'll try to formalize the concept of slightly broken higher spin symmetry. And the mathematical structure I will need is called strong homotopy algebra, or L-infinity algebra. And then if you construct this L-infinity algebra and prove a couple of structural statements about the number of parameters you have, the number of correlation functions, this can prove 3-dimensional bosonization duality. Okay, so that's the plan. And yeah, the first point on the plan is to introduce this family of 3-dimensional conformal field theories. They're interesting because they describe actual physics in 3 dimensions. For example, on the right, you see the typical phase diagram of some substance like water, for example, and the red point is so-called critical point. So at critical points, we know that a bigger symmetry emerges, conformal symmetry. So the behavior of physical system near the critical point is described by some conformal field theories. Because everything happens in 3 dimensions, we need 3-dimensional conformal field theories. And on the left, you have this lambda line, which is a line of superfluid transition in liquid helium. There is one remarkable property of second-order phase transition, so-called universality. For example, the universality class of the critical point on the right, it also includes what's called uniaxial Ising model. So it has the same critical indices. The water has exactly the same critical indices as a uniaxial magnet at the Curie point. And on the left, we have superfluid transition, but the critical indices are the same as in the planar magnet, where the magnetic spins can rotate in a plane. But all of this is described by some three-dimensional conformal field theories. So I will slowly introduce them. So we'll start with something that is very simple, which might be in textbook, but it's not. I mean, the first line is, of course, in textbook. This is just free scalar field. And if you drop the mass, it's a free conformal field theory in any dimension, in particular in 3 dimensions. But some of the properties that this simplest theory has, they will remain to be true within 1 over n expansion for highly non-trivial interacting models, like the ones that describe the second-order phase transitions. So let's have a look at this model as a conformal field theory. Of course, we have fundamental field phi, and to make story more interesting later, let's take phi to be in fundamental of UN, or can be ON or any other group, but for now, for simplicity, let it be UN. Okay, so we know there is a field phi, and because we are in 3 dimensions, it has a free conformal dimension 1/2, and the next to the phi operators are so-called single trace operators. These are some bilinears in phi, and again, because later we'll jump to anti-de Sitter space through holography, it's nice to consider UN singlets among these bilinear operators. And there we find the first one, which is a scalar field, dimension 1. Then there is a current, a U1 current, dimension 2. There is, of course, stress tensor, which is what tells you you're dealing with conformal field theory. But on top of this, if you take S derivatives and distribute them over 2 fields in the right way, you get a conserved tensor whose conformal dimension is exactly S plus 1. And having a conserved tensor, of course, is a signature of some symmetry. And because you have conserved tensor of every rank, there must be some infinite dimensional symmetry. And of course, it's also extension of conformal symmetry, which is generated by the stress tensor. So by default here, we already have some infinite dimensional extension of conformal symmetry in 3 dimensions, and we usually call it higher spin symmetry. But the problem here, or maybe some small disadvantage, is that this symmetry is too strong. So it's infinite dimensional, but it's too much. You can, while we see that in free conformal field theory, you have conserved tensors of arbitrary rank, the opposite is also true. If you find some conformal field theory in dimension 3 or higher, then it's a free CFT. So higher spin symmetry is a bit too much to have non-trivial models. So let's make the story a bit more interesting by introducing phi to the force interaction. So on the left, that's a standard way. You just write phi to the force, and we go to 4 minus epsilon dimension, as Wilson Fisher suggested. Or you can also do 1 over n expansion. So you can consider the number of components of phi to be large, and there is standard trick called Hubbard-Stratonovich, where you introduce auxiliary field called sigma on the right to simplify 1 over n expansion. So now it's very easy to count various orders in 1 over n. So in any case, if you look at this theory in the large n limit, which will be relevant for holography, what you find is very reminiscent of what we already had on the previous slide, which was this. So the big difference is that the scalar operator, which was phi squared, its dimension jumps from 1 to 2 plus 1 over n corrections. But that's the only difference for now. You still have global symmetry currents, stress tensor, and you have higher spin currents, which are conserved to the leading order in 1 over n. Of course, they cannot be exactly conserved. They develop some anomalous dimensions, but they're suppressed by 1 over n. And yeah, so to the leading order, it's very easy to compute these anomalous dimensions. Was done maybe 40 years ago. And for now, state of the art is that you can do the next order 1 over n squared correction, but that's already 5 loop that was done recently. That's it. So we have a spectrum of single trace operators that is not very much different from the free scalar. But of course, everyone except for global symmetry, current, and stress tensor, they develop non-trivial anomalous dimensions. Yes. Yeah, it's the same as a phi squared. Yeah, it's exactly the same. Why do you need 5 loops? It's because the loop of phi contributes n. So there are some many loop diagrams that you can write, which on the other hand are suppressed by 1 over n because every vertex has 1 over n, but they're enhanced because you have closed phi loops. And it turns out that if you want to pick up next order 1 over n squared, the highest diagram you can draw is 5 loop. So I mean, orders in 1 over n is not exactly the same as loop order. So 1 over n expansion is more complicated. You can have many loops while still fighting with like 1 over n squared. Okay, so the next to the simplest theory, the first one was just free scalar. The next one is free fermion. So again, we are in 3 dimensions. It's a very simple theory. And of course, it features higher spin currents. And again, the spectrum of these single trace operators looks very similar. So we have a scalar operator, psi bar psi, whose dimension is exactly 2. And I want to stress that it's very reminiscent of what we have here. But here we have some non-trivial 1 over n corrections, but in free fermion CFT, of course, we just have this s plus 1 for a rank s tensor, which doesn't get any corrections. So everyone is conserved. It's a free CFT. Of course, it has higher spin symmetry, which you can somehow derive by constructing charges from these conserved tensors. And the most important point here is that the spectrum of these operators is very close to the spectrum of the critical boson of Wilson-Fisher or Ising. It's also called critical vector model. And let me point out that this model, has matter which is scalar, and free fermion is fermion, but the spectrum look the same. But of course, CFTs are not the same. If you compute correlation functions, they're different. And here you also have non-trivial 1 over n corrections. Here you never have them. So they look similar, and people noticed this many years ago, but they're not the same, obviously. So at this point, there is not much you can say about this similarity. And of course, there is also interacting version, which I introduced already with this Hubbard-Stratanovich trick, sigma. So it's psi bar psi squared interaction. It's called critical fermion Gros-Neveu. And this theory looks very similar to the very first slide, because the dimension of this psi bar psi operator is 1 plus 1 over n correction. So it's actually very similar to free scalars. So again, we have a CFT, which is built from scalars. We have CFT that is built from fermion, but the spectrum of single trace operators, they look very much alike. And again, the leading 1 over n correction is easy to compute, but the next order state of the art now, it's a 4 loop calculation. So now, yes. Sorry, which epsilon? Yeah. In this, it's a dirty trick of epsilon expansion. So whenever we do 4 minus epsilon or 2 plus epsilon, in this case, yes, of course, you want epsilon to be 1. And of course, none of this perturbative expansion converges. You need to Borel resum or maybe use some resurgence. But people were quite creative in kind of extracting actual anomalous dimensions from these expansions. But usually, as with any asymptotic expansion, if you don't go very far, you get very good approximation. It's just important not to go very far. Then you need more elaborate techniques to extract reliable answers. Yeah, so epsilon is 1. Yeah, and also you said correlators are not the same. Of course, yeah, the not of course, but correlators are not the same. So if you literally compute correlators, I don't know, in free scalar and in Gros-Neveu, they are not the same, but I'll talk about this later. Yeah, they're not the same. Yeah, they're not the same. So these are clearly different CFTs, but there is some similarity. And what allows one to actually make them, to relate them, is Chern-Simons. So because in 3 dimensions, we have this luxury of having Chern-Simons action, so we can spice up these models in the following way. So we take 4 of these matter theories: free scalar field, phi to the fourth, free fermion, and psi to the fourth. We gauge the global symmetry, say UN in this case, and to make dynamics of the gauge field interesting, we add Chern-Simons interaction. Now the following should be clear. By the way, I use blue and red to distinguish between boson and fermion. So the following should be clear, that because of having this Chern-Simons interaction, in general, these theories break parity. Well, they describe some physics like Ising model, but it's not relevant right now. They have in general 2 parameters: the number of fields n and Chern-Simons level k. And in fact, what emerges in the perturbation theory is a kind of 't-Hooft effective coupling, which is lambda n over k. And it should be clear that if you take k to infinity, which is lambda 0, then the only thing Chern-Simons term does is it asks you gently to consider gauge invariant operators, because essentially with the level taken to infinity, Chern-Simons interaction decouples. So you just have flat connections over which you need to integrate. So basically, you just need to consider gauge invariant operators. The point I'm trying to make is that whenever lambda is 0, which means k infinite, you're still dealing with your old conformal field theory that I introduced here, but you are asked to consider only singlet operators in there, because they are gauge invariant. Yes, and the most important thing for me is that on the space of these 4 theories, there are dualities, and the most remarkable one, because it survives in the larger limit, was called 3-dimensional bosonization duality. It was maybe 2011 when it was discovered or conjectured. So how it works? So we have 4 theories. So those in blue, they are built from scalars, and those in red built from fermions. And line starts whenever lambda is 0. And in principle, because n is large, this lambda is almost a continuous parameter. So you have a continuous family of conformal field theories. The conjecture is that these 4 theories are in fact just 2 theories. So you can take free boson gauge symmetry at Chern-Simons, and if you take level small, well, if you dial lambda to infinity, then your CFT will look exactly like a gross Neveu model, another way around. And anywhere in between, they also coincide. So these 4 theories, the conjecture is that these 4 theories are just 2 theories. And then I think the name 3-dimensional bosonization explains itself, because you have pairs of theories. One is built from scalar matter, another built from fermionic matter, but they should describe the same physics. What it means in practice, they should have everything the same. All OPE coefficients must be the same, anomalous dimensions, correlation functions, everything must be the same. Once, well, you identify this lambda and n, the 2 parameters you have appropriately on both sides of the duality. So that's a conjecture, but it's a conjecture. There was no proof. Yes. Yeah, in principle, yes. So n and k are like integers. But if n is large, k is large, lambda is continuous, almost continuous. So in the sense that you can forget that it's like rational. These are big rational numbers, big in the sense numerate denominator. So it's almost continuous. But in principle, yes, you're right. So there is a kind of specialization or detailization of these dualities whenever n and k are small. Then there are some funny jumps in Chern-Simons levels that you can that you need to take into account. But yeah, here it looks a bit simpler. And there are other dualities, but these dualities, fermion, and boson, they don't survive in the large n limit. So this is the most non-trivial duality. There's papers, for example, by Zeiberg et al., Witten, Aroni, that introduce these other dualities more systematically, and also for small values of n and k. But for me, lambda is continuous. N is large, lambda is continuous. It will be clear from holography why it has to be the case. Okay. You mean this duality? Yeah, I mean, of course, you have 2-dimensional bosonization duality, but it has little to do with this one. So in a sense, the name is obvious, right? If you relate 2 CFTs build fermion boson, you should call it bosonization. But I would say in 2 dimensions, bosonization is kind of simple. I can literally write a formula how it works. Here you cannot. Moreover, what makes story difficult is that it's not phi or psi you're relating. Phi and psi are not even gauge invariant operators. So in fact, let me jump to the next slide. The simplest gauge invariant operators are exactly these higher spin tensors. They're at least bilinear in your matter fields. So you can construct these phi many derivatives phi or psi many derivatives psi. So these are the simplest gauge invariant operators. And they're conserved to the leading order in 1 over n, which as I try to argue is a signature of some infinite dimensional symmetry, which we call higher spin symmetry. But of course, in these CFTs, there are many other operators. You can take kind of J with J in derivative, and many others. There are infinitely many operators. Even the number of J is infinite because you have one J per every spin. All of them have some correlation functions and anomalous dimensions, conjectures that everything should be the same. And the problem to prove it or even to check is because in order to check bosonization, you need all orders in lambda. And if you look at how perturbation theory and these Chern-Simons meta theories look like, you need all orders. Well, in order to have all orders in lambda, you need to resum infinitely many diagrams. So this is kind of weak, strong duality in a sense, because to see bosonization duality, you need to be able to travel from lambda 0 to lambda very large, and this requires infinitely many diagrams. So all calculations, as a matter of fact, if you want to see duality, all calculations are very complicated in these conformal field theories if you try to start from Lagrangian. But there is one simplifying assumption that we can make is, well, it's not an assumption, we have a proof immediately. Since all other gauge invariant operators appear in like repetitive operator product expansions of higher spin currents, it's just enough, sufficient to concentrate on higher spin currents. So if we manage to prove that all correlation functions, anomalous dimensions, and so on of higher spin currents coincide on both sides of the duality, so we prove, because as a matter of principle, correlation functions, anomalous dimensions, and all other operators can be extracted from these ones. So let's concentrate just on these higher spin conserved tensors. Dean. Yes. Can you just argue that they are the same based on bootstrap? No, people tried. There is a couple of papers, in particular by Al-Dai. You can extract some information, but I mean, it's not cure-all. So Bootstrap doesn't allow you to prove these dualities. No, you need to, I'll tell you what people tried, which was like more efficient. So I think Bootstrap is just generic technique. So to prove something, you need something more targeted to the problem, not a generic technique. So Bootstrap is useful, but it doesn't give you everything you want. So you need to combine Bootstrap with something else. So the question is what's going on in these Chern-Simons meta theories, because when they were free, we clearly had this higher spin symmetry, which I'll define properly later. But for now, we just, well, we can think that we have this infinity of conserved tensors, so there must be some symmetry. But because these models are interacting, higher spin currents cannot be conserved. But because we're dealing with some conformal field theory, what stays on the right of non-conservation equation cannot be just some random thing. It has to be an operator in your CFT. And if you count these quantum numbers, the spin and conformal dimensions, there are not so many things you can write. So basically, on the right of the higher spin current, there has to be a composite operator that is built either from the product of two such things, or in some exceptional cases from three of such higher spin currents. So in the sense that higher spin currents are responsible for their own non-conservation. And this is exactly what allows to close the loop in the logic. Otherwise, like the worst possible case that you can have is that your current is not conserved, but its non-conservation is given by some other random operator that you have no idea what it is, so your symmetry is gone, so just forget about it. So here we are in a more lucky situation because the current is not conserved, but it's not conserved in a very specific way, which is determined by the currents themselves. So one can put it to some practical use, as people did. What? You go to the large end and you just count spins and conformal dimensions, so that's the only thing you can write. Why not put because spin and conformal dimension don't add up. So you just get something that is way off. So I mean, it has non-conservation has to have the right spin. So the spin has to be s-1, but conformal dimension s+2 to the leading order. And okay, they go in the opposite direction, so to say. It's really hard to build something that has so few indices with such dimension. And it turns out that very simple counting tells you that, okay, there is a finite number of terms you can write. I think if you take something like spin 4 current, then the only thing that can stay on the right is a product of stress tensor and scalar operator, and there is nothing else. Yeah, so it's it's very poor. I mean, even though maybe the formula looks a bit big, but I mean, there are very few terms actually you can write on the right-hand side. And okay, but current's still not conserved, so we have no idea what it is. But nevertheless, it's not an abstraction to using this non-conservation. This is exactly what Malta-Senergy did. So they wrote the most general ansatz for non-conservation of the current. Because current is not conserved, charge is not conserved. So the action of charge on the current modifies, and they wrote some general answers for that as well, and used information about just kinematics of the problem about this structure of three-point function. Because usually people say that conformal symmetry constrains three-point functions up to a number, but in fact, if you have tensor operators, that's not exactly true. It constrains them up to a finite number of numbers. So if you consider three-point function of stress tensor or higher spin current, there are three structures which are conformally invariant and conserved that you can write. Two of them are very easy to find. You just take free scalar CFT or free Fermat CFT, write expressions for higher spin currents, compute three-point functions. They are different. So you have two independent structures here. What is less obvious is that with some help from epsilon tensor, you can write third one, but there is no force. So any three-point function of conserved higher spin currents, including stress tensor, has to be sum of three structures with some coefficients. But because we consider here 3 times infinite family of correlation functions, you can imagine infinitely many phenomenological parameters that can stay here, depend on spin, and be some random numbers. But what happens to be the case here is that if you impose this non-conservation inside correlation functions, you can find that there are only two phenomenological parameters. One is just an overall factor that I dropped by putting this approx sign. And there is another phenomenological parameter called theta here, which enters in a very simple trigonometric way. So, and in particular, we can see bosonization in this formula, because if theta is 0, then two structures on the right die off. You just have correlation function equal to that in free boson CFT. Now, if theta is pi half, then the first and the last, they die, and you have correlation functions of free Fermat CFT. And of course, you can interpolate between them, you have this theta. So what is important here is that even though currents are not conserved, so you don't have symmetry, but still the way you don't have the symmetry is very useful, because this not symmetry constrains your correlation functions in such a way that they can only depend on two parameters. And this also proves three-dimensional bosonization duality at this order, at the level of three-point functions, because this is a result that is obtained without any information from this microscopical realization through Chern-Simons plus Lagrangian. So this is consequence of some weird symmetry. So therefore, it doesn't matter what these currents are built from. In any CFT that has certain properties, correlation functions should look like that, which proves the duality. But of course, the question, natural question to ask here is, what is the right mass? Because it's clearly not a symmetry, and it would be nice to understand it in a more systematic way. But up to now, what we know is that this slightly broken higher spin symmetry, whatever that is, seems to work. And people try to use basically the same arguments for higher point functions, also for anomalous dimensions. This is what we did some years ago, and everything seems to work. But would be nice to understand it a bit better on the mathematical side, and also prove it in some way. Yes.
When you send n to infinity, how simple the theory is? So it's not beyond the.
So if you send n to infinity, still correlation functions, you see, they don't coincide with free scalar or free fermion. So if you have this Chern-Simons interaction, there is still this term, and there is specific linear combination of the structures. So it's still it doesn't you don't see yet anomalous dimensions in this formula, but already 3-point functions. The structure is not that of free CFT. For generic theta is not free CFT, even though it doesn't have like complicated conformal dimensions or anything. But correlation functions are already non-trivial. So in
that level,
yeah. It's very non-trivial, because still, if you want, so theta related to lambda by very complicated formula, and if you want to travel from 0 to pi half, you still need all orders in lambda, which means infinitely many Feynman diagrams from the Lagrangian point of view. So the calculations are really hard even in this limit.
And that formula about the value of J equals 1
Mm-hmm.
It's exact one in large N,
and
it doesn't depend on
so in principle, you have these coefficients here that should depend on lambda in a certain way. Yeah, I think, okay, so this formula as it is an exact formula for all n, in the sense that even in the Ising model, you can find higher spin current, it's not conserved, and there is some combination like here. But then operators, because it's a small n, you really don't know what JJ in brackets mean, because it's a composite operator, but yeah, deducing its property is complicated. But in the large n, fixing, yeah, you can use certain tricks to find a dependence on lambda. In fact, this will be more clear from holography or from what I'll say later. But from first principles, from Lagrangian, it's not very easy.
So let's say for large n, despite you have another coupling constant, still, let's say, dimension of operator GS1, GS2 is the dimension.
Yeah, it's the sum. It's the sum. So in a way, well, it's a consequence of 1/n expansion. So you can so anomalous dimensions, they are suppressed. All anomalous dimensions, they are suppressed by 1/n. So to the leading approximation, you can still use the simple rule. So they just add up.
They don't depend on
Anomalous dimensions. No. I mean, there is a non-trivial 1/n expansion, but the leading order doesn't have any lambda dependence, so to say. Maybe this is what you asked. Yeah. So, but subleading they do. So yeah. Okay, so that's the story on CFT side in a bit from pragmatic perspective, how we can do some calculations without asking too many questions, like what is the right math. So let me jump to the bulk, to anti-de Sitter, which is going to be 4-dimensional anti-de Sitter space. Okay, so then the standard edges CFT rules, they immediately tell you that if you're looking for something that is dual to vector models, this has to be a theory with massless higher spin fields. Why that? Because you have infinitely many of higher spin conserved tensors, and they're dual to gauge fields in the bulk. So stress tensor is dual to graviton, global symmetry current is dual to photon. Likewise, if you have conserved rank S tensor, the dual field in edges 4 is going to be some massless, hence gauge field with spin S. So now the question is whether we can have a theory that is dual to Chern-Simons vector models. Then instead of tedious quantum calculations with this Chern-Simons metal Lagrangian, we can just do the standard edges CFT tree-level calculation of diagrams and derive all correlation functions and so on. This is what John Bean started, but there were some abstractions. So the best proposal back then was in the form of Vasiliev equations. But then we realized that they're a bit incomplete in the sense that these are nice equations, but they're not yet in the form you need for holographic calculations. There are some ambiguities in how to extract actual interaction vertices, or you can put it as there are infinitely many free parameters. So, and this problem hasn't been solved along these lines. Independently from all of these, people, in particular me in the audience, they try to reconstruct holographic dual just from conformal field theory, because we can try to ask the question, say, for free CFT, what type of interaction I need to write in anti-de Sitter space so that the correlation functions are exactly the ones I have, say, in free CFT. And then there are some arguments along these lines that tell you, as well as explicit construction, that tell you that these theories are very, very non-local. So it should be hard to construct them anyway. There are other ideas by Jevitsky, Malakoha, Aroni et al., who also try to be maybe more systematically reconstruct something from CFT. All of these are nice ideas. I'm just thinking about this pragmatically, that it's hard to extend any of these as to incorporate Chern-Simons meta theories. So there is something that you can write starting from free CFT, but how to turn on this lambda parameter or Chern-Simons coupling is not yet known. Nevertheless, it was very useful to think of this higher spin gravity dual, and this is how people came up with this idea of three-dimensional bosonization, because they took these theories, CFTs, they thought, okay, what they're dual to, some higher spin gravity, but they're dual to the same theory, maybe they're dual to each other, and so on. And then you can drop this holographic card whatsoever and just try to prove this on CFT side. But I'm going to do something in the bulk. And completely independently of all these holographic stories, we developed with Mitya, based on early papers by Mitsayev, we developed a theory that looks like the right one, but it was in flat space. So it has nothing to do with any holography a priori. So it has the right spectrum of higher spin fields with spins from 0 to infinity. It's in flat space, and then, okay, you can think that this is some higher spin extension of both self-dual Yang-Mills and self-dual gravity. You can show that it is at least one loop finite. It's integrable in flat space. And then later we constructed covariant equations of motion, which you can also extend to anti-de Sitter or de Sitter space. And it's hard to tell what this looks like in anti-de Sitter space without having more time, but it's very easy to define this theory in flat space, because in flat space, every Masters field has 2 degrees of freedom. So if you go into some unitary gauge like light cone gauge, it's represented just by 2 scalar fields that kind of account this helicity plus S, helicity minus S degrees of freedom. So you have a normal kinetic term, and then you have some cubic interactions. Then it stops. That's the beauty of the theory, that at least in flat space, all interactions stop at the cubic order. And if you extract cubic amplitude, it's the standard textbook one that is written in spin or helicity language downstairs. So the only thing that higher spin symmetry does, it fixes the relative coupling between fields of different helicities to be this 1 over gamma sum of the helicities. And then there's some smooth deformation to anti-de Sitter space. And now we're talking because we have a theory that has the right spectrum to be dual to Chern-Simons meta theories, but it's not because it's too small. So the story in the bulk look as follows. At the free level, all theories like this thing chiral that we constructed, and obviously there's also anti-chiral. At the free level, they all look alike. At the cubic level, chiral and anti-chiral interactions, which I think is obvious from this formula. You know, there are 2 types of brackets, angle and square ones, and all cubic amplitudes, they are either in terms of square or angle brackets in spin or helicity. So at the cubic level, chiral and anti-chiral interactions, they cover all possible types of interactions that you can construct. At the quartic, there is some gap in between. This green region represents full higher spin gravity dual of Chern-Simons meta we want to construct, but we can't. And okay, we have these 2 chiral, anti-chiral pieces going in both directions. But there is already some information that we can extract just from existence of chiral theory in the bulk, because if you have theory in the bulk, you can, and it's nice, it's perturbatively local, you can just go and compute holographic correlation functions, you find something that looks like a CFT. And then this implies a certain consequences for Chern-Simons meta theories, because you just literally invert this picture and apply it to Chern-Simons meta theories. And now, just from the very existence of chiral and anti-chiral theories, you know that inside Chern-Simons meta theory, you have hidden closed subsectors, which you can also call chiral and anti-chiral, which define new conformal field theories. And that's the first consequence just from the very existence of a new theory. You get free CFT. And but there are useful consequences, namely, you can literally prove three-dimensional bosonization duality up to at least 4-point functions from the very existence of these chiral theories. Let me sketch some argument. So remember that in 4 dimensions, massless field has 2 degrees of freedom. So every massless field is basically 2 scalars representing helicity plus minus s. Likewise, on CFT side, if you solve a conservation equation inside every current, including stress tensor, there are 2 independent functions, in fact, 2 independent functions that you can also associate with something like helicity plus s minus s operators. And we also have this one-to-one dictionary, therefore, between everything. So we have, on one hand, 3-point correlators of tensor operators. On anti-de Sitter side, we have cubic vertices of massless fields. And because there is a smooth deformation for all of them from Minkowski, we have the spinor helicity amplitudes, and everything is in one-to-one. And we can try to apply this concept of helicity to CFT and do the following trick, which I will illustrate just for the 3-point function of stress tensor. So let's take 3-point function of stress tensor. There has to be certain expression in terms of graviton that computes stress tensor 3-point function. Say, let's start from free CFT. In order to reproduce stress, well, 3-point function of stress tensor in some free CFT, now Einstein-Hilbert action is not enough. It gives you some mixture of 2 free CFTs. In order to kill that and get something that is pure, you need to add wild tensor cube or Riemann tensor cube with the right coefficient. So this is the action schematically on the right that is due to free CFT. So it's Einstein-Hilbert, but enriched with wild tensor cube. So now let's write this in terms of spinor helicity. So we have just free Einstein-Hilbert action, which is phi box phi, because we have 2 degrees of freedom, helicity plus 2 and minus 2. Then there is a cubic interaction, plus plus minus and minus minus plus. They represent just Einstein-Hilbert cubic vertex, and plus 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 and minus minus minus, they come from wild tensor self-dual, anti-self-dual pieces cubed. Now, the first piece comes from chiral theory. The second piece comes from anti-chiral theory. And from this chiral theory perspective, there is no parameter that you can insert in here because these theories are unique. So you can drop one field, you can add a new parameter inside this theory. These are like bricks that you can use to construct something new. And so we can try to add up these 2 pieces. And in order to get something that is unitary but maybe parity violating, the only thing you need to do is to perform some phase rotation, like electromagnetic duality rotation, on these components. And then as a result of this manipulation, what you get is something different. It will have Einstein-Hilbert action, I mean, truncated to the cubic order. And there will be this parameter theta that stays in front of something that is parity even. It has plus here, and but you will introduce a new piece which is parity odd. So you find some new theory on anti-de Sitter space that have an additional parameter, and this parameter is responsible for gluing chiral and anti-chiral pieces. And this is what allows you to derive 3-point functions in Chern-Simons meta theories for any theta starting from some pure theory like free CFT. And if you generalize this argument, then you can put it in the following way, that the very existence of chiral higher spin gravity implies 3-dimensional bosonization duality. I mean, at the level of 3-point functions, you can literally prove uniqueness and so on, but you can also push this argument up to 4-point correlators. Of course, we don't know a certain part of our theory we don't know, but if you think that in a way, say from your action, we know the quartic piece, and okay, it consists of chiral, anti-chiral pieces and something in between, we can still perform this phase rotation to get some 1-parameter family of correlation functions. But as a matter of fact, so from these calculations, we got all 3-point functions in Chern-Simons meta theories, and that was actually the first time higher spin gravity had something new to say. because usually people consider duality with free CFTs, and about free CFTs you know everything. And because calculation and Chern-Simons meta theories are very complicated, we knew some pieces of three-point functions before that, but the first time complete expression for three-point function was written was exactly by using this trick of gluing chiral and anti-chiral pieces together. Okay, so this is a 0.5 proof of bosonization duality in the sense that the very existence of this theory implies a bosonization duality. At 3 point, that's 1-to-1. At 4 point, you can't prove uniqueness of your correlation functions, which would be even stronger, but you can easily prove that there is a one-parameter family of conformal field theories interpolating between free ones. Okay, so that's, yeah, I think that's the end of the bulk story. So it's a bit incomplete at the moment because, well, we have the two wedges here, but don't have the middle part. Yet you can derive certain useful consequences from duality. And what is helpful is that something that is highly non-perturbative on safety side, which is this parameter theta, which, well, to get it right, you need to sum infinitely many of diagrams. But here it appears kind of as a simple phase duality rotation. So at very low cost, it comes from the bulk. But then the problem is to get higher order correlation functions for which you need to know the full higher spin gravity dual. Okay, so we can derive some useful consequences, but not the full proof of the duality or all correlation functions. Now let me explain more formally. Yes.
This argument by Malvesen and Jabayeva, that is on the slide. Well, one can say it also proves bosonization duality at large at 1/n.
Yeah. So all of this is in to the leading order in 1/n. So I mean, yeah. So the thing is that they had this very nice paper, but I think, I mean, from if you read it, what they've done, they looked at some specific correlation functions or families. So in fact, you never find in their paper expression for all three-point functions. In particular, this odd piece is missing. And then in this paper that I mentioned with Jomby and Pals, we found a bit more of three-point functions, but still not all of them. And the first time you have complete expression for all spins and so on was from chiral higher spin gravity. So even though, I mean, this modus energy Bredov argument does prove, but it does prove within the set of correlators they considered. And
anyway, like the set of correlators, you see that there are not more than this amount of solutions which are parameterized by single parameter.
Yeah. And it's very easy to prove that because we know that this chiral theory is unique, so you can't do anything with it. You just need to learn how to glue them together. But there is no internal parameter that this theory have. I mean, except for this overall coupling constant. But there are no internal parameters, so there can be only external, kind of allowing you to glue two pieces into consistent solution. And
I'm wondering why considering bulk is advantageous, because it seems like this expansion decoupling constant, it goes over to 1/n on the boundary.
1/n is basically the same. So in the sense that for us, 1/n is in the bulk is the usual perturbative expansion. On CFT it's large n. But the problem is that if you want to get theta or lambda, that's infinitely many of diagrams on CFT and nothing in the bulk. It's just a parameter of your theory, which already kind of very non-perturbative in terms of this lambda. Because I mean, you can use this bulk as a kind of phenomenological thing. You just have two parameters. You can identify them with CFT. I mean, if you know some information, but you don't have to. You have these parameters for free because they're just present in your theory. But on CFT side, you really have to deal with infinitely many diagrams to get non-trivial answers that are applicable to all thetas from 0 to pi half. Okay, so bulk is over. So let's jump to CFT side and try to understand this higher spin symmetry better. And the antonym to slightly broken is very unbroken, but we usually call it just higher spin symmetry. what it is once again. So let's start again with some free CFT, for example, free scalar or free fermion, and observe that we have this infinity of conserved tensors. Obviously, you can construct a charge, like, for example, stress tensor gives you not one, but many charges corresponding to all generators of conformal symmetry. Even more generators you can get from higher spin tensors. But what kind of symmetry they're responsible for? Well, yeah, the one result that I mentioned is that if you have a conformal field theory in dimensional 3 or greater with stress tensor and at least one higher spin current, you can prove it's a free CFT, maybe in disguise. In 3 dimensions, there are 2 choices. You either have free boson or free fermion. And you can, yeah. So let me define this symmetry a bit better. So let me start from conserved tensor. Out of conserved tensor, we can construct a current, which is done by contracting tensor with what is called conformal Killing tensor, which is the same formula as for the stress tensor, but with more indices here. So you construct a current from tensor, from conserved tensor. You integrate it, you get a charge. Charge for free fields that we have here, it looks something like this. So it's a dagger A and some differential operator in momenta in between. And these charges form an algebra. This algebra, of course, contains conformal algebra SOD, 2 as subalgebra. But what's special to free conformal field theories is that this Lie algebra is in fact obtained via the usual commutator formula from some associative algebra. And the way to understand why you have associative algebra is this. So suppose you have free theory, free conformal field theory, for example. Then we know what it means to have conformal symmetry. So you just have some transformations where V is a conformal Killing vector, and d minus 2 over 2 is obviously the free dimension of phi. And if you apply this formula to box, you see that it maps solutions to solutions. This is what means to have conformal symmetry here. But because your CFT is a free one, instead of taking commutator of 2 such transformations, you can just multiply them. And this way, you obviously get some high derivative operator. For example, this is example of a symmetry. So you have epsilon here, which is a constant tensor. Many derivatives, obviously, it commutes to the box. So it's a symmetry. And there are more non-trivial symmetries here that don't commute with the box. But essentially, what you see is some infinite dimensional associative algebra of symmetries. And if you take the commutator, then inside the Lie algebra constructed via this Lie bracket, you should find conformal algebra. So therefore, there are many ways to explain what this associative algebra is. So it's either the algebra of symmetries of some free equation, or you can understand it as some deformation quantization problem, or as a quotient of universal enveloping. There are many ways, but say in 3 dimensions, which is relevant for us, the way to realize this infinite dimensional algebra is through the usual 2-dimensional harmonic oscillator. So you have 2 pairs of a dagger. You construct bilinears out of those, they form SP4. SP4 is the same as 3-dimensional conformal algebra, so 3, 2. And if you take all functions of a dagger that are even, then you have some infinite dimensional algebra of, let's say, observables in 2-dimensional harmonic oscillator. And this algebra is associative, contains conformal as a Lie subalgebra. So that's one way. But or like this, you just take symmetries, multiply them, you obviously get some infinite dimensional associative algebra. These algebras are called, well, in our community, they're called higher spin algebras. Let me check the time because there is no clock. Yes, I think 5-10 minutes. So there is yet another way to understand what it is, maybe, which is more transparent. So let's view this wedge as a phi of x, and maybe the arrow going up is like some jet kind of expansion, derivative expansion of this phi. Now, if we impose a Klein-Gordon equation, then it cuts out certain region out of this. So the solutions of Klein-Gordon equations are sitting in a smaller wedge. And then symmetries are by definition linear maps that map solutions to solutions. So if you view free scalar field as a representation space of conformal algebra is just vector space, you have some infinite dimensional vector space, all maps on this vector space, they're symmetries. So they map solutions to solutions, which is a bit tautological because we are in solution space. So therefore, roughly speaking, if you know what this vector space is, which is a free scalar field as a representation of conformal algebra, then all matrices, all endomorphism of this space is what higher spin symmetry is. And then it's also clear that they form associative algebra. It's clear that with every endomorphism associative algebra, there is a Lie algebra associated via the usual Lie bracket equal to commutator and so on. And okay, there is some miracle number 2, which I'll skip. So now we can move next. So we had conserved tensor, we constructed current, we analyzed the symmetry of charges. So this can be done from many different perspectives. You always, of course, get the same algebra, which I tried to define in several ways. Now it's reasonable to ask, who are correlation functions here? Well, there should be some invariants, in particular of conformal symmetry. And it turns out that these associative algebras, again, if you view them as matrix algebras, it's very easy to imagine that they have some kind of trace operation on them, and they do. And this is what allows you to construct invariants of the higher spin symmetry. And well, by default, invariants, of course, don't know what you want. So if you consider trace of some matrices A, B, C, D, it's invariant under commutator symmetries for any matrices. But if you want to compute correlation functions, you have to take them to be of some special form to represent these quasi-primary operators. But this calculation can be done. So it's not an abstract formula here, which represents correlation functions as invariants of the higher spin algebra. This can be actually computed, which is what we did for any n, and I'm just giving 3 and endpoint examples here. So Q and P are certain conformally invariant tensor structures. There's some prefactors. It's not important who they are at the moment, but it's important that one can get a very simple closed form expression for generating function of all conserved higher spin currents. And this you can obtain by computing invariant of the higher spin symmetry. And of course, because higher spin symmetry contains conformal algebra, they are also invariant on the conformal symmetries. And in principle, you can just outsource it to a student because in free CFT, you can do just simple weak contractions, but simple weak contractions will never give you these beautiful formulas easily. But nevertheless, okay, this is not very deep because these are correlation functions in free conformal theory. So now, can we do better? And before I'll try to explain what slightly broken symmetry is, let me summarize the higher spin symmetry, which is unbroken part. So in every free CFT, we have infinitely many higher spin conserved tensors. They generate charges that are called Q here. By constructions, charges generate an infinite dimensional Lie algebra, which we know, in fact, to come from associative. And this is infinite dimensional extension of conformal symmetry. Now, charges form an algebra, higher spin algebra. Currents, all currents from 0 to infinity, they in fact furnish a single irreducible representation of this algebra, which I denote by this formula, Qj is J. And the fundamental field of your CFT phi is another irreducible representation of the higher spin algebra. And then, yeah, there is miracle number 1, that in fact this Lie algebra is associative. And every free CFT defines for you some associative algebra. And there is miracle number 2, which in fact you can see that the space of higher spin currents is in a way formally equivalent to higher spin algebra itself, but it's not important exactly how this happens. But what will be important for the proof of three-dimensional bosonization duality is that if you go to 3 dimensions, because everything I said works in any dimension except for 2, but if you go to 3 dimensions specifically, then you'll find that higher spin algebra free boson and free fermion are isomorphic. So that's exactly the same higher spin algebra, and it happens to have 2 inequivalent representations, which is free scalar and free fermion. but the algebra is the same, and you can also represent it as Weil algebra, the algebra of A dagger. And then you can show, and that's one thing, that there is unique family of invariants, these traces I showed to you, of this algebra. Okay, now let's try to explain slightly broken higher spin symmetry. So what we have to do is to explain the following. So currents were conserved in free safety. They form charges. Charges form an algebra. Algebra acts on the currents. So currents form a reducible representation of the algebra. Now it's not the case. So currents are not conserved, but non-conservation is driven by the currents themselves. Charges are not conserved as well. So action of charges on the currents get deformed in a certain way. And then you can ask, okay, what is the right mathematical structure that takes all of this into account? So clearly what we have here is not just deformation of the higher spin algebra as an algebra, or it's also not a deformation of its action on a certain module. It's two things together. So you kind of, you have to deform the action of the algebra together with the algebra, with the module. So the right mathematical structure that does this is a strong homotopy Lie algebra or L-infinity algebra. So what you have to do, I mean, you have to introduce so-called higher brackets, higher multilinear structure maps that deform the action of your symmetry represented by some parameter psi here. And also the commutator of two symmetries doesn't close exactly here, which would be just commutator in the higher spin Lie algebra, but it can have certain corrections thanks to the module. So that's kind of the only mathematical structure that allows you to incorporate this idea that you need to deform Lie algebra together with action on some module of it, not just the algebra and not just the action, but two things together. So you can construct such an L-infinity algebra, some technical work, but what's important is that you can prove certain structural statements about this algebra. So as Dirac showed many years, that higher spin algebra of free boson and free fermion are the same. Of course, he did not formulate it in exactly this language, but this result is equivalent to that. Now we can prove just by analyzing Chevalier-Lindbergh cohomology of this higher spin algebra is that there exists exactly one invariant of this algebra to serve as an endpoint correlator for free or large n limit. And in fact, this is what I showed to you. This invariant can be computed to give the right correlation function. So the idea seemed to work. Now, if you jump to this L-infinity deformation, then you find that L-infinity depends on two additional parameters, which are not present in the higher spin algebra itself, and they can be related if you want to this K and N in microscopical realization. Also, you can show that invariants, they can be deformed as to remain invariants of this L-infinity algebra. They are unobstructed, so certain cohomology vanishes, they are unobstructed. And there is also closed form formula for these guys, which looks pretty much like one loop correction somewhere. But I don't want to like decode all the structures here, but there is a simple generating function for all these invariants in terms of a certain new associative product. And well, that's pretty abstract, but if we believe that it is the symmetry, it is the right symmetry, then this is the proof, because we could show that there is unique family of invariants that should serve as correlation functions in these models. But there is a simple consequence of this not very constructive proof at the moment. There is a simple consequence following from some technology here, that all correlation functions, they should have very special form. It should be finite sum of certain fixed structures times this cosine and sine things. So it's not always happens that you have non-trivial dependence on the coupling constant that has this form, because you can imagine correlation function just to be very complicated function of your coupling constant. But here you have sum of finite number of fixed structures times this cosine and sine things, and this agrees with all results obtained so far. Okay, so this implies three-dimensional bosonization duality because we're never asking what J are built from, scalars or fermions, as long as we have some higher spin currents. and there is a unique deformation of this higher spin symmetry present in free CFT to L infinity algebra, and then it features unique family of higher spin invariant structures. So this also formalizes the concept of the slightly broken higher spin symmetry. So let me summarize all these stories. Okay, that's a bit of a joke. So higher spin symmetry is a kind of three-dimensional Virasora, but it acts in a completely different way because Virasora is just normal Lie algebra, and it's good enough to be just Lie algebra to give you lots of interesting models. So higher spin symmetry acts in a completely different way. It should be understood as this strong homotopy algebra, and therefore the right language to deal with this is of some high cohomologies of this higher spin Lie algebra. Then uniqueness of L infinity invariance implies three-dimensional bosonization duality and also makes this simple specific prediction for their structure. And yeah, as a matter of fact, we have kind of new type of physical symmetry because we have a physical model. Let me come back to the beginning of the story, like Ising and all that. So we have physical models where L infinity is well, acts on physical operators, because L infinity is quite a popular structure in certain topics, but it usually kind of it's used to for formalism. It's used to formulate certain things in a beautiful way, but it's usually not a physical symmetry acting anywhere. So here it is a symmetry acting on physical operators. Of course, a natural question is whether we can push it beyond large N, whether we can make it more constructive by actually computing this invariance beyond the leading piece that we computed. And I can also speculate that if you go to the opposite limit, not large N, but very small n, like n equal 1, then you go to the Ising model and you see that anomalous dimension of spin 4 current is very small. So you have 0.2 instead of 0 here, and it gets smaller and smaller as spin increases. So in fact, in the Ising model, you seem to have slightly broken higher spin symmetry as well, but whether you can put it to some practical use is less clear. And a couple of more things here is that if you jump to anti-de Sitter space, then we see that chiral, the very existence of chiral higher spin gravity implies that you have some hidden subsectors in Chern-Simons vector models, and it would be really nice to identify them directly on the CFT side. So of course you can just compute holographic correlation functions, but it would be nice to understand who they are just on CFT side. Yes, and I told you that the very existence, again, in practical terms, it proves three-dimensional bosonization 3-point. It gives you one parameter of correlators at 4-point. But a speculation I want to make is, in fact, if you try to push it to higher orders, then three-dimensional bosonization is because we have this theory. If you try to prove it holographically, you don't need to know the full theory to prove three-dimensional bosonization duality. You just need to know that it features certain subsector that is closed. And there is something completely orthogonal to that, is that people in the past, they discussed tensionless strings on edges for CP3. And the way it goes is that strings on edges for CP3 are dual to Abbe-J theory, which is some kind of Chern-Simons matter with bifundamental matter. And in this theory, where your matter fields are matrices n by m, if you take these matrices to be very tall or very long, they look like vector models. So vector models are due to higher spin gravity, and inside this not well-defined higher spin gravity, we have again chiral higher spin gravity sitting inside. So it means, if you trust all of these dualities, it means that inside tensionless strings on edges for CP3, there is again some closed subsector that would be nice to identify. So, but that's a bit orthogonal to everything else I said, just a speculation. So I stop here. So thank you for your attention, and I go back maybe somewhere here. Thank you. Like this one.
So maybe you can ask yourself if there are some questions. So there are some questions here, or
are there any questions online or offline?
Yeah, maybe one.
Okay.
Okay, so we know that if we have an L-infinity algebra, we can construct a field theory out of it, right?
Yep.
What is a field theory which is associated to your L-infinity algebra? It seems to have your high-spin algebra in the sector. Well, you should have these gauge fields of high-spin algebra plus something more, right?
Yeah. So the thing is that you don't have any field theory. So in a sense that it's ill-defined. I mean, the idea here is to use L-infinity as a symmetry on safety side, and then it seems to
work. I
understand.
But then you forget about everything. You take this L-infinity algebra and build a field theory out of it.
Yeah, I think you get something not very well defined as usual.
Non-local, right?
Yeah, probably it will be like completely meaningless as usual.
So some kind of
so I think so what we see is that the same problems that we have on Edia's side, like these field definitions, non-locality, and so on, they're just not present on safety side. So you can do these things. Your setup is much smaller. So therefore, there is no chance of making similar mistakes on safety side that than we make on Edia's side. And in particular, the proof of the concept is this calculation of n-point functions, because you can go on and compute this higher spin symmetry invariance. They give you all n-point functions in these free limits, but there is no way you can do this on anti-de Sitter side, because you don't have any theory.
No, but even if you don't go to anti-de Sitter, just on the boundary,
yes,
you can take this L-infinity and consider
this is what you're asking. Okay, yeah. This is a very good question. I actually don't know. Yeah, so I think so our
it seems to have with this background conformal fields high spin.
Yeah, you should find something like this, but then I don't know what happens. Yes, it's a very good question. Yeah, because again, maybe there is a way to avoid some of the usual field theory problems with higher spins, thanks to conformal symmetries here. So I don't know. Yeah, that's a very, very good question. Any other questions? Miti is asking, are there any other questions? Miti, do you have any other questions?
So do you understand correctly? So you had some R in the formula of transformations of
okay, yes. Mm-hmm.
Would it correspond to in terms of the CFT?
Yeah, it's inversion. It's a kind of inversion map that flips ket into bra into ket, and that's what allows you to identify endomorphisms with just V tensor V tensor V star with, I think there was actually a formula here, which is a bit schematic, So it's higher spin algebra is the endomorphism algebra, and higher spin currents are just, bilinear operators here. And if you know the map, how V goes to V star, which just requires some non-degenerate bilinear form here, then you can identify both spaces. So in a way, higher spin currents is the same thing as higher spin algebra.
Okay, this I understand, but I meant like you start from infinity, you read the infinity format, and then you get an infinity structure, right? And to the best of my understanding, you did it to some leading order in something.
No, there's closed formula for all orders, and in several different forms. There is a closed formula.
But then does that mean that you can construct also traces?
Yeah, there is also closed formula for traces. Yeah, that's was written schematically here. Like there is some product in this deformed higher spin algebra that I never defined, and if you compute trace log, that's exactly generating function of this invariance, and it starts with the usual trace that we all know, and then there are some corrections.
So essentially, you know the exact answer.
Yes.
Or you keep correlators and all this.
Yeah, but I mean, the problem is that invariants know nothing about what you really want. Like, okay, these are invariants of higher spin symmetry, but you need to compute them on the right object to get correlation functions, because a priori invariants, I mean, think of them as matrices. You have trace A, B, C, D. If you don't take A, B, C, D to be the right objects, yes, you compute invariant, but it's not going to be correlation function you're looking for. It will be invariant, but not the right one. So yeah, I think that's why it's not yet constructive, because one still needs to sit down and to actually compute them. But there is a closed formula. Yeah. Yeah, it is sort of broken, but it's broken. It's difficult to say how. So you have small L infinity algebra, which is yeah, this is the term that physicists came up with, but it doesn't represent the actual reality, because it's not a symmetry. Because by symmetry, I mean what we usually understand. So you have some Lie algebra, Lie group, and say your multiplets, they form certain representation of Lie algebra. This is not what's happening here. To the leading order, yes. To the leading order, you have higher spin Lie algebra, and it acts on this higher spin currents. And this you can encode by 2 bilinear maps, and then you can check that, yes, Lie algebra with its module is the same thing as some L infinity algebra, the tiny one where you have only bilinear maps. But now something else is happening, that you deform this small L infinity that has only bilinear maps, you deform it to actual L infinity, which has multilinear maps. And then, okay, it's L infinity algebra. So somehow algebra gets deformed together with representation on which it acts. This is how you can maybe interpret it in more physical terms. Like you deform both things together rather than just algebra or just its action. And then they obviously get entangled. So the kind of currents, they back react on the charges and so on. So it's yeah, it is a symmetry, but it's also, yeah, maybe one can say that just historically it's clear why maybe 50 years ago it was hard to come up with this, because it's not the symmetry that acts as a symmetry. So it's something infinite dimensional that is useful and constrains correlation function, but it's not a symmetry from the usual textbook point of view. It's not a Lie algebra acting somewhere. Yes, I'm kind of deforming it, but I'm deforming it in the category of L infinity algebras. I'm not deforming it in Lie algebra category modules. Yeah, that's the idea. Yeah, so I think the name is nice, slightly broken higher spin symmetry, but it's kind of a bit wrong, because it's not symmetry in the usual way, but yeah, people thought, okay, it's broken, but broken in a useful way, so they call it slightly broken, because it's just some terminology that Maldas and Zhibredov came up with. So they yeah, I think, yeah, if current is not conserved and equals to something else, okay, symmetry is gone. But the idea was that what it is equal to is built from the currents themselves, from some composite operators built from the currents. So maybe it's still useful, and they proved the concept that yes, even though it's not a symmetry, this still constrains correlation functions. But this is how. So in fact, you have L infinity, you can construct invariants of L infinity and so on.